Okay. Thank you very much. So first, I'd like to begin by thanking the organizers for inviting me and giving me the opportunity to talk in this workshop. So the work I'm going to talk about today is based on work in progress that was done with Leonardo Rastelli, Brandon Ahun, and Matteo Sacchi, and will hopefully be published sometime this year. Is it okay? Can you hear me?
I'm in the front, I can't tell. Sounds like. Okay, if you're in the back and you can't hear it, don't raise your hand. If you can't hear, raise. Okay, let's see. Yeah, I guess someone will complain.
All right.
It seemed like it's off, but.
Okay, sorry. I can't tell from here. All right, so yes, can begin. Why is it not working? Oh, okay. I guess that's it with that. All right, so hopefully I don't need to take this in this context, but dimension reduction is a rather useful tool in studying field theory problem, particularly because it leads to various, I would say, peculiar relations between different field theories. A particular interesting instance of this is under referred to in modern as AGT, referred to some mysterious relation with partition functions of different theories, that we kind of understand them as both theories having the same higher dimensional origin. Now, the most well-known example is a correspondence between a 4-dimensional or a 2-dimensional theory, or 3-dimensional theory. It is usually attributed to the quantification of some 6-dimensional underlying theory. In this case, we're going to talk about something similar but somewhat different. We're going to take a higher dimension to be a 4-dimensional SCFT. We'll compactify it on the surface, and that will lead to a relation between two different partition functions of two different 2-dimensional theories. But we specific higher dimensional theory we're going to take a look at will be the H0 SCFT. What we're actually going to do, we're going to exploit this idea to try to understand its reduction on 2-dimensional surfaces. I will also briefly mention generalization to other cases. Right, so you can ask, why is it a useful thing to consider? There are various reasons why it is an interesting problem to consider. First, dimension reduction itself leads to various interesting field theory phenomena and allows us to understand various field theory phenomena. First of all, it might be able to understand 2-dimensional theories and dualities between them. 2D theory is also specifically simple that you might hope that you can learn something from their behavior on the original 4-dimensional theory you started with. Finally, this relation between partition function is also quite useful. It gives you a new tool to compute partition function by computing them actually in different 2-dimensional theory. All right. So the outline of this talk is going to be as follows. I'll begin with some introduction. The majority of it will be devoted to various disparate aspects of dimension reduction that are going to be useful in this talk. Then I will move on to briefly review some aspects of the H0 SCFT and its compactification that again are going to be useful in this talk. After that, I will go on to discuss how we can conjecture the 2D models we reduce the H0 theory on particularly punctured spheres. Then we're going to talk about testing them with various consistency checks. And finally, I will end up with some conclusions. All right, so the general theme of this talk will be dimension reduction. So briefly, what is dimension reduction? Consider a quantum field theory living on some large d space-time dimension. We can take the space-time dimension to be some d from some smaller d dimension, Euclidean space, times m, where m is some compact manifold. The reason why this is interesting is you can now consider the limit where the size of m goes to 0. In that limit, we expect the theory to be effectively described by a potentially new quantum field theory living only on the small d space-time dimension. This idea is called dimension reduction. It allows you to get new quantum field theories in lower dimension from some given higher dimensional theory. Now, the properties of the resulting lower dimensional theory will then depend on the original chosen higher dimensional theory, but also on property of the compact surface M. This allows you to give various learn some non-trivial phenomena about the lower dimensional theories if you sufficiently understand the higher dimensional theory or property of the compact surface M. So to give again some examples that I'm assuming are quite familiar, most of them to the audience here, but I will repeat them anyway. Probably the most well-known example in this class is the reduction of the 62,0 theory on a torus you get n equal to 4 superangles. Of course, the hallmark of this reduction is that the complex structure moduli of the torus become the coupling constant of n equal to 4. Now, as is well known, complex structure is defined by a modular transformation cyclically describe the same torus, which then imply that coupling constant of n equal to 4 different with coupling constant different by a modular transformation are cyclically equivalent. This is the S duality of n equal to 4 superangles. The interesting thing is that the S duality of superangle is a non-perturbative phenomenon. It is not that easy to understand just from perturbative physics. However, here it's basically motivated simply from geometrical properties of the torus. This is one of the usefulness of dimension reduction to allow us to understand non-perturbative statement of the lower dimensional theory from, in this case, simple geometrical properties of the compact surface. Now, this idea then we try to generalize in various directions. The simplest generalization is to just keep the 2,0 theory, but change the torus to some more general Riemann surface. This, of course, leads to the well-known class S construction, where you engineer for the n equal to 2 theories by compactifying 2,0 theory on Riemann surfaces. And this idea has been very useful in our understanding of the landscape of 4D n equal to 2 theory. First of all, in its ability to generate new n equal to 2 theories that don't have an n equal to preserving Lagrangian and are therefore very difficult to access in either more traditional methods. Usually, you can learn a lot about the properties, like various dualities between different 4D n equal to 2 theories. Following this, you naturally want to generalize radial direction, and one natural generalization is to reduce the supersymmetry. In that case, you can try to reduce from 62,0 to 61,0, and then similarly reduce the lower dimensional supersymmetry to 4D n equal to 1. These ideas have been explored quite a lot in the recent years. In fact, there are more references than I should probably fit into this slide. And basically lead to many definitions you see from 4D n from classes can also be generalized in discrete. And you can understand, you can learn a lot about properties of 4D n equal to SCFT. For instance, discover new dualities between different 4D n equal to 1 theories. For that, you can try to also reduce the dimension in which you're working and try instead of 6 dimensions to go to lower dimension. For instance, you can try to look at 5D SCFTs, reduce them on Riemann surface to get 3D n equal to 2 SCFTs. And this has also been explored in some of the references here. And again, similar phenomena have been observed in 4D equal to can also be observed in this class. So we generalize in very similar way. Now, this naturally leads to the idea of trying to go to the next step and then reduce one more dimension and go to 4D n equal to 2 SCFTs and reduce them to dimensions. This may even appear more natural in some sense because we kind of understand 4D n equal to 2 theories much better than we understand 5D or 6D theories. In fact, there are several 4D n equal to 2 theories principally described with a weakly coupled Lagrangian, so that you cannot do in higher dimensions. So this seems to be a far maybe simpler program than compactifying high dimensional theories, and yet it's surprisingly very little is known about this case. Now, there are various cases that have been worked out, and in fact, there are quite a few references even that I can write here, but it's almost exclusively devoted to compactification on spheres with no puncture. Once you go on to surfaces with punctures or to higher genus Riemann surface, relatively little is known. Almost nothing is on compactification of 4D n equal to 2 theories on higher than genus Riemann surface or with punctures. So what we will try to do today is try to make at least some progress in the direction, and we consider the compactification of a specific 4D n equal to SCFT, in this case the H0 SCFT, on Riemann surfaces, either punctured spheres or more general higher genus, particularly punctured sphere, but talk a bit about also higher genus Riemann surfaces, to try to get to the 2,2 theories. All right, so before we go into this, one thing that I should probably say. So as usual, when you do dimension reduction, you want to preserve some supersymmetry. To do that, you need to do a topological twist. So you need to introduce a background connection to the R symmetry and make it equal to the spin connection on the surface, or that will cancel for some of the supercharges. Normally, you can preserve at most half the supersymmetry, and if you do that, at least in higher dimension, that thing is unique up to some choice of the embedding. In 4D, it's a little different. You actually have 2D, even if you want to preserve the maximal amount you can preserve, there are two different ways to do that. That has to do with the fact that the R symmetry is not just single group. You have an SU2 part and you have a U1. There is a different depending on that you want to couple to the U1 part or to the SU2 part. This will change the number of the supersymmetry you preserve in 2D. You can either preserve 2,2, in which case you want to embed the connection inside the SU2 part of the R symmetry, or you can preserve 0,4, where you embed the connection inside the U1 part. Here we're going to concentrate on compactification to preserve 2, 2. So in particular, we're going to topologically twist using the carton of the SU2R symmetry. All right. So before I'm going to go to the actual details of how we're going to try to understand this compactification, I should first want to see several aspects and reviews about something aspect of dimension reduction. The first one I want to say is a little bit about how the properties of the higher and lower dimensional theories are related in dimension reduction. We're going to want to start with symmetries. So an important property of physical theory is its symmetries, and of course the associated Tooth anomalies that you can solve with a symmetry. In dimension reduction, there is a natural relation between the symmetries and the Tooth anomalies of the higher dimensional and lower dimensional theory. It's easiest to express this relation for continuous symmetries, in which case the anomalies can be embedded in an anomaly polynomial, which is a form of dimension 2 higher than the dimension of the spacetime. Then the relation can be given as follows. The anomaly polynomial of the lower dimensional theory is given by taking the non-polynomial of the higher dimensional theory and integrating it over the compact surface. In this case, the symmetries and anomalies of the lower dimensional theory are kind of determined from those of the higher dimensional theory, but also depend on the compact surface which enter through this integration on it. Now, I should say a couple of comments about this. First, there is also a generalization of these two discrete symmetries. We integrate the anomaly theory rather than the anomaly polynomial. I will not talk about this here at all. Here I will only concentrate on continuous symmetries. Second, there are a few loopholes in this argument. First, you can only learn the anomalies from symmetries that originate in 60. If you have something that arise accidentally in lower dimensions, you cannot learn the anomalies in this way. Additionally, if for some reason the anomalies under some symmetry vanish, that symmetry may end up acting trivially. So if the anomalies integration gives you some native anomaly under that symmetry will be there and will be inherited from the high dimensional theory. But in circumstantial cases, if the anomalies vanish, then it's possible also the symmetry that won't be there. All right. So talking about the relation between symmetries, we can think about a slightly more general relation between the operator of, particularly the BPS operators of the lower and higher dimensional theory. Now, the idea in this relation is the following one. Consider some BPS operator in lower dimension. Now, BPS operators are annihilated by some of the supercharges. The supercharges in the lower dimensional theory are inherited from the higher dimensional theory. So we expect that if you have some BPS operator in lower dimension, it should come from some BPS operator in higher dimensions. Furthermore, this reduction includes a Klein reduction. So in general, whatever operators you have left in lower dimension come from some zero modes over on the surface. It says you might be able to predict the BPS operators you have in lower dimension by looking at the spectrum of BPS operators in high dimension and counting their zero mode on the surfaces. Now, however, in practice, this is usually pretty complicated because the number of zero modes of a surface is dependent on the geometry of the surface. It can change continuously under various deformations. However, if you concentrate instead of the actual number of zero modes on various differences between them, then it's possible that they'll be protected. But there are certain differences related to the index of operators that are counted by the Artiasian index term, and therefore the topological properties of the surface. These are then protected and are much easier to count. To give some simple example, the number of zero mode of a left moving or right moving Weil fermion is not protected. I can obviously change them continuously by introducing a mass, but the difference is protected because related to the index of the Dirac operator. So you can then ask, okay, if this is some protected quantity, it should match some protected quantity in lower dimension. And there is a natural object protected quantity associated with BPS operator in lower dimension. And that is the contribution of this operator to superconformal index. Superconformal is a certain counting of the BPS operator spectrum such that if they can merge to lower multiplet, they sum to zero. This is therefore protected quantity deformation. And it's natural to expect that this sort of sum of zero mode will be related to contribution of the superconformal index. So it turns out that this idea works. And the general idea it leads to that you can kind of predict the contribution of BPS multiplet to the superconformal index of the lower dimensional theory based on the BPS spectrum of operators in the higher dimensional theory and various topological properties of the surface. Now, this idea has been mainly used in quantification of 6D and 5D SCFTs on surfaces. Here I will briefly state some of the results you find from this. So usually it's been used particularly for ubiquitous BPS multiplets that are quite common in these theories and are very easy to identify. So there are two types that fall on this category. One is the energy momentum tensor, that basically every SCFT should have one and just one energy momentum tensor, so you kind of always know it's there. Additionally, our conserved code multiplet, whenever you have a continuous flavor symmetry, you know that you have them, and precisely in the adjoint representation of the flavor symmetry. So again, since we usually also know the flavor symmetry of the SCFTs, this is usually pretty easy to infer their existence. Now, what it turns out when you do this procedure, again, I'm just going to tell you the result. I'm not going to actually say how you actually do the computation. But it turns out that this energy momentum tensor leads to contribution of the index at integral to 3 g-1 marginal operators. Only for conserved code, you get something similar, but you get just g-1 marginal operators. Now, if you have some familiarity with dimensional reduction, and this idea might sound familiar, it's usually quite expected if you reduce a theory on a surface, then the complex structure moduli of the surface will become a marginal operator in the lower dimensional theory. This is basically what this thing kind of tells you. It's also known, but somewhat less appreciated, that if your theory has a global symmetry, you can put an holonomy of the global symmetry around the cycles of the surface, which will then lead to g-1 marginal operators. We can think of it as coming from the conserved coordinates. So in a sense, what I'm saying here is kind of known already in dimensional reduction, but this viewpoint provides a somewhat different way of motivating it, can particularly allow you to generalize it to other direction, as I'm going to do soon. Now, before that, there are a few comments I do want to make about this. First, here I'm concentrated on the reduction on genus G Riemann surface without puncture and without flux, beside the twist, and I need to preserve supersymmetry. Now, it's possible to generalize to the inclusion of flux. It's not that complicated to do. This will generally change the number of operators, particularly for conserved coordinates. It usually doesn't affect the energy momentum tensor because it's not charged on the flavor symmetry. Now, punctures is a little bit more complicated, and I currently don't know what the generalization is if you want to include punctures. Another issue is the argument I mentioned so far was suggestive, but of course was not a complete proof. There are various loopholes involved. For instance, I assume that if I have a BPS local operator in lower dimension, it comes from some local BPS local operator in higher dimension. But it's possible for it to come from some extended operator instead. As such, there can be deviation from this expectation. And particularly, it has been noted experimentally in various cases of quantification, particularly from 6D and 5D, that this sort of prediction works at least for sufficiently large genus of flux. But there are deviations from them, especially for small values of the genus. Right, so, this expectation that I mentioned, that the superconformal index would have contribution of 3g-1 marginal operator, and also g-1 for every conserved current. So g-1 the adjoint of the group. This works at least for sufficiently large genus. If we start looking at small genus, usually you can see a deviation from these predictions. Right? Now, finally, when you do the superconformal index, you need to choose an R symmetry that you will use as your superconformal R symmetry. Here I'm assuming that this statement assumes that the R symmetry you use is the UVR symmetry. So when I'm saying that you get marginal operator, of marginal operator, it assumes that this UVR symmetry is the superconformal R symmetry in the IR. This, however, in many cases is not the actual case. In which case, you will still see this contribution, but they will not actually contribute as marginal operator, but might contribute as relevant or irrelevant. Again, it usually doesn't affect the energy momentum tensor because it's uncharged under any flavor symmetry. So even if there is some mixing with another symmetry, it will not affect it. But it can affect conserved code, which sometimes gives you relevant or irrelevant operators instead. All right. So far I talked a lot about reduction from 6D and 5D, but in this talk I want to talk about reduction of 4D. The reduction of 4D, there are actually new type of CFTs of BPS operators you can consider. And particularly, there is a new kind of relatively ubiquitous BPS operator you can consider, which are Coulomb branch operators. Now, it is found that any interacting 4D n equal to SCFT has a Coulomb branch, and therefore these operators are as ubiquitous basically as an energy momentum tensor. And once you go to 4D, unlike higher dimension, they actually are BPS operators. And as such, you can actually ask what happened when I reduce them to on a 2-dimension on a surface. What sort of contribution to the 2D index can I expect from these operators? Again, I'm going to just briefly tell you what we find, and I'm going to refer to the papers for the details. In here, I'm going to consider a 4-dimensional Coulomb branch operator of dimension delta. What you can argue is that in lower dimension, you will get contribution to the elliptic genus from this operator of 2 twisted chiral fields, with R, sorry about that, with R charges R delta and delta minus 1. So recall I'm compactifying to get 2, 2 theories in 2D. You have a left moving R symmetry and a right moving R symmetry. So here I represent the R chart that this one will be the left moving R chart and this one is the right moving R chart. Twisted chiral have the property that the R charges are, the left and right one are related by a sign. So if one of them is delta, the other one is minus delta. Right, so you get two of them. One with R charge is the dimension of the Coulomb chart, the other one dimension minus 1. Additionally, there's a multiplicity of the contribution in the index, which will be 1 minus G. Right. Again, I know this is the contribution that you get to the index or the elliptic genus in this case. It's not necessarily mean that you actually have a twisted chiral, and particularly if G is larger than 1, its contribution will be negative. But twisted chiral will usually contribute positively. All right. So now I'm going to move on to something else. I'm going to discuss puncture at least briefly. So as is common in dimension reduction, you can in many cases introduce punctures. And we are going to do that here. Of course, if you want to do this puncture, you kind of want to also be able to define them in a somewhat better way. No, how can I define them? How can I study them to understand some of their properties? There's a particularly common way to do that, which I'm now going to briefly describe. So I'm going to look at some puncture on the surface, and I'm going to zoom into this puncture. Locally, it will look like some long tube that ends on the puncture. I can consider reducing on the circle. In which case, I reduce my original height dimension to on the circle, and I just get the theory on the interval that ends on the puncture. The puncture then becomes some form of boundary of the theory reduced on a circle. I can then define it as boundary condition on the height dimension reduced on a circle. For instance, if you have 2, 0 theory, if you reduce on a circle, you get 5D maximally symmetric Young-Mills theory. So punctures in the 2, 0 theory classes are usually can be described as boundary condition of 5D supersymmetric Young-Mills theory. Now, in that case, and in many other cases, the theory is described by Lagrangian, and therefore I can describe the boundary condition by giving the Neumann boundary condition to the fields I have in Lagrangian. For instance, for the case of the 5D supersymmetric theory, a common boundary condition is to give Dirichlet to the vector and Neumann to the adjoint chiral, in which case your 5D gauge symmetry just become a global symmetry. It's the global symmetry to do with the puncture. Now, this idea is useful for several things. At least two main things that we can learn from it that will be useful later on. One is you can learn about the contribution of the puncture to the anomalies. As was mentioned also yesterday in the talk by Alessandro, puncture, when I mentioned the contribution to complete the anomalies from integration of the surface, this was just the contribution of surface without punctures. If you have punctures, the punctures add additional contribution, kind of degrees of freedom localized on them. This contribution can also be evaluated from the boundary condition. They're basically given by half the contribution of the field receiving non-boundary condition. You can just see that if you have an interval that ends with the two boundaries, then whatever received non-boundary condition on both sides will reduce to the lower dimension, and then for the anomaly should come along from the two boundaries, and each one will therefore contribute half. One other thing that you can learn from this is you can learn how to glue punctures. Specifically, if I have two punctures, I can glue them together, in which case I basically eliminate the puncture and just have one long tube without the boundary. This basically eliminates the boundary that I've given. Now, at the boundary, I have boundary condition. In particular, the field receiving the Dirichlet boundary condition will then be killed and will not survive to lower dimensions. However, when I glue, there is no longer a boundary, so this field should not longer be killed. The way you normally do it is when you glue, you have to reintroduce the fields for which you're given the Dirichlet boundary conditions. For instance, in a 2, 0 theory, you usually give Dirichlet to the vector. If you then want to glue the punctures, you need to reintroduce the vector, which basically means you gauge the global symmetry with the puncture. This is the usual gluing prescription in classes. All right. Finally, I want to come into the AGT relation, which, as I said, will play some interesting role in this talk. So what is the AGT relation? To illustrate this, I'm going to consider some higher dimensional theory that I'm going to call T. And so I'm going to reduce it on a product of two manifold M1 and M2 so that they fill the entire spacetime of T. I can then do this reduction in two steps. I can reduce first on M1, which I get some theory that I'm going to call T1, and then I can reduce T1 on M2. This last reduction can be thought of as the partition function of T1 on M2. And then I can reduce to T first on M2. Now I get some other theory that I'm going to call T2. I can now reduce it on M1, which will be the partition function of T2 on M1. Now, you might expect the order of limits shouldn't matter. You might expect there's some relation between the partition function of T1 on M2 to that of T2 on M1. This relation is generally called by now HGT, based on Alday-Gaiotto-Tachikawa, which found the original relation for which this T was the 62,0 theory, M1 was some Riemann surface, so the T1 was some class S theory, so with the reduction of 2,0 on the Riemann surface, and T2 turned out to be the 2D Toda theory. Then there's some equivalence between the S4 partition, and M2 was S4. There's a difference between the S4 partition function of some class S theory and various sigma correlators of the 2D Toda theory. Right? Now, there has been various attempts to derive this relation. Particularly, this kind of tells that reduction of T of 2,0 on S4 should be the Toda theory. There's one attempt to derive this thing. I will not talk about them in detail. I will mention some brief and interesting fact that will play some role next. Now, if you're familiar with it, you can define, if you have a 4D n equal to 2, you can define a chiral algebra. There's some protected sector, that's what is usually with the Schur operator, the two-dimensional chiral algebra. There's a similar structure also in 2,0 theory. You can also define a chiral algebra, and it turns out to be equivalent to a W algebra, which also is the chiral algebra to the Toda theory. So this is kind of consistent with this idea, because you can think of the S4 partition function, you can do it in the omega deformation. The omega deformation will localize when you put the theta on S4 with the omega deformation, you localize the theory on the origin, which essentially localizes the theta on a two-dimensional plane, where you expect the chiral algebra to live. So this idea is kind of consistent with that. Again, it's not a proof, but it's kind of consistent with the idea. So the main reason I'm mentioning this is that we are now going to do something similar, but we're going to start with a four-dimensional theory. So the idea is that we're now going to take our T to be a 4D n equal to SCFT. I'm going to take it to be the H0 soon, but for now I'm just going to consider it to be a general 4D n equal to theory. I'm going to reduce it on S2 times sigma. So before I can do it in 2 steps, I can first reduce on some Riemann surface that I call sigma. I will get some 2D theory, the compactification of the original 4D n equal to theory on that surface. The second action will give me the S2 partition function of this two-dimensional theory. The other thing I can reduce on the S2, I expect to get some 2D theory whose sigma correlator will be equivalent to the S2 partition function of this T1 theory. The natural question is, what will be this 2D theory? And the natural answer to it that we're going to propose is this is going to be the chiral algebra of the 4D n equal to 2 SCFT. The logic is somewhat similar to what I mentioned previously. You can kind of think of doing this S2 partition in the omega background that will localize to the origin. So you kind of localize your 4-dimensional to some 2-dimensional plane. In particular, if you also involve it within the U1R symmetry, you can do it by preserving 0,4 supersymmetry, which is the supersymmetry that's preserved by the chiral algebra. So it's kind of seems natural to expect that something like this is going to work, and that kind of like the AGT dual for a foreign quantity will be its chiral algebra. Here I'm going to assume this works. I'm not going to assume it works, and what we're going to do is going to try to use this to understand what is this T1. Particularly, we're going to assume it works. We're going to try to find some T1 that with S2 partition mimics the correlator of the theory on this side, and use this to understand the compactification of 2D theories on a surface. Of course, in order to do that, you kind of want to choose your original 4D SCFT so that this will be particularly simple. So you want something that is a very simple chiral algebra so you can easily compute its correlators. And for that, we are going to take one of the simplest SCFTs known, and this is the H0 theory, basically the minimal RGRS Douglas theory. The nice properties of it is its chiral algebra is the Liang minimal model. So just a two-dimensional minimal model, and therefore it is relatively easy to work out. Right. I should, of course, mention that the chiral algebra in general is a non-unitary 2D SCFT, 2D CFT, while the T1 theory of expect from T1 should be some unitary SCFT, and such this kind of suggests a correspondence between the S2 partition function of a unitary theory and correlators of a non-unitary theory. Hence why we call it a unitary non-unitary correspondence. Yes.
Find the chiral algebra, you don't need a sigma. It's just defined for the theory. So where does sigma enter?
Oh, we don't need a sigma here for the chiral algebra?
We never depend.
No, it won't depend. The sigma enters through this line.
Say that whatever this theory is, it has the S2 partition function.
The S2 partition function of T1 will match the sigma correlator of its chiral algebra. So the sigma enters to depending on which partition function of the chiral algebra you need to kind of look at. It's similar to our it's kind of similar to how AGT works, right? You always have the 2D total theory on the other side. The 4D theory kind of changes what partition function, what correlator you need to look for the total theory. Yes.
There are two ways to use the system. The other one is one. And if you use the system, then the 2D theory is unitary. And you are saying that if you use U1, then 2D theory is
No. It doesn't depend on when on the which one you're using. Here I'm compactifying on sigma with the SU to our twist.
very few.
That will get us unitary. You can also do the compactification on some sigma with the U1R twist. That should also get you unitary. There are some cases that worked on the S2, and there are some unitary theories you get at 0,4 theory. So it's not necessarily. Here it's a little bit problematic to do that because we're choosing also the H0, and for the H0, the Coulomb branch is not fractional, so U1 twist is not going to be well defined.
Whether you get the non-unitary chiral algebra depends on the partition.
It has to do with the way you do the reduction on the S2. Any other questions?
Yeah, I'm still confused. If you reduce H0 on the sphere, and if you reduce H0 on the torus genus G, you always get the same T1. That's what you're saying?
No.
So T1 does depend on sigma.
T1 depends on sigma, yes.
Okay, so that was my question. But then you say that T1 is the.
I'm saying that the S2 partition function of T1 is the sigma correlator of the chiral algebra. So changing sigma will first change T1, and therefore change the S2 partition function, but it will also change the sigma correlator.
Yeah.
Okay. I understand. I'm also tired. Any other questions? All right. So if there are no other questions, so before actually going to all the details, well, at least some of the details, I want to say a few things about the H0 theory that are going to be useful for us. So the H0 is in some sense the simplest for the interacting n equal to SCFT on account of the fact that it has the smallest, I think it has the smallest non-central charge among the interacting theory, n equal to 2 SCFTs. It has a one-dimensional Coulomb branch spanned by operator of dimension 6/5, and that will play a bit of a role later on. It has no X branch and no continuous flavor symmetries. So basically, beside the Coulomb branch operator, the only other known BPS operator is the energy momentum tensor. There are, of course, there are probably higher one. It will even kind of study the spectrum, but it will not play an important role here. I written on the central charge. It will play a brief role, but I don't expect to remember them. Now, as you can already see from the dimension of the Coulomb branch being fractional, it has no manifest n equal to preserving Lagrangian, but it can be realized as an higher fixed point of n equal to 1 only preserving Lagrangian, just under Maruyoshi and so on, almost 10 years ago. As I also mentioned, its chiral algebra is the 2D Liang model. It's a non-unitary minimal model. Its central charge is this value. Being unitary model, a minimal model, it possessed only a finite number of highest weight representation of Eros algebra. In particular, this model possesses only 2 of them. One is trivial, associated with the identity operator, and there is only one non-trivial operator in this theory that I'm going to specify by sigma, and has dimension of -50. Right. Before discussing the reduction of H0 on more complicated surface, it's convenient to start with reducing H0 on a circle. The reduction of H0 on a circle is turned out to be known and relatively simple. It is simply given by a single free twisted hyper. At least if you go to the d pi r. Now, if you don't go to the d pi r, when you keep the radius finite, the situation is a bit more complicated. In that case, there turn out to be 2 singular points on the compact Coulomb branch. Well, locally around each point, the low energy theory is still a free twisted hyper, but they slightly differ by the sister action, or particularly by how the four-dimensional U1 action is embedded inside the SU2 that rotates the two chirals inside the twisted hyper. Specifically, I've written them down here. So you have point A and point B. Here I've written down the R charges in terms of the 4D R symmetry for one chiral and for the other one. So for one point, these are the R charges. For the other point, these two are the R charges. Okay, so why am I mentioning this? One interesting thing that this can tell you is it can teach you about puncture associated with the H0 theory. As I mentioned, puncture are given by boundary condition for the theory I've reduced on a circle. So we took the H0, reduced it on a circle. The theory we have is a free twisted hyper. So you can define puncture by just giving boundary condition for the free twisted hyper. So you can give Dirichlet to one chiral and Neumann to the other chiral. Here I'm going to make the choice that I'm going to give Neumann to the one with the higher star charge and Dirichlet to the one with the lower star charge. However, you have 2 points that you can use to define the hyper, and that means there are 2 distinct punctures you can define depending on which point you use. Both of them, the field theory look like a free twisted hyper, but they differ by the U1 charges. And this will mean that they differ by, for example, the charge of the chiral that you're going to use to glue them, and also by the anomalies that the puncture will contribute to these symmetries. I will also now mention some other fact that might appear mysterious, but turns out to be true. There is a one-to-one correspondence between these points and operators in the Liang model, where this point A associated with the identity operator and point B associated with this phi operator. This, as we will soon see, is quite natural from the correspondence we mentioned, and it's happens to be important for this correspondence to make sense, among other things. All right. So
these punctures are where? These punctures are where is it? It's living on Riemann surface.
Oh yeah, I can introduce punctures on the Riemann surface. I can normally think about them as some specific boundary conditions. So I can either give the punctures with the identity element or punctures with phi. It turns out that this puncture with the identity element is equivalent to having no puncture. So there really is only one sort of with phi, which is the really non-trivial one, and this is equivalent to having no puncture. There are various reasons that I will show later why it's kind of useful to think of them as 2 distinct punctures. Even though for all practical purposes, this is equivalent to just having nothing. All right. So now we're going to actually start to consider how to engineer the 2-dimensional theories we get for induction on the Riemann surface. Here I'm going to be very schematic and very brief. So I'm almost going to ignore completely all technical details. I'm just going to present broadly how the computation works. So this is particularly also mean that I'm going to ignore a significant number of subtle issues that appear in this computation, or which are really reserved to the paper for this. All right. So the idea is the following. We want to understand. Here I'm going to specifically start with the 4-punctured sphere. It turned out to be the simplest one to start with. So again, various technical issues. You're going to want to find a 2-dimensional theory that you get when you reduce H0 on a 4-punctured sphere. So it will be a sphere with these 4 phi punctures. We expressed from the previous correspondence that the S2 partition function of this theory should be equivalent to the correlator, in this case, the correlation function with 4 phi operators of the Liang model. Notice that we have a choice of which puncture we want to put here, and there is a choice of operator we want to put here. So in this case, this correspondence is quite natural that every puncture corresponds to some operator of the Liang model. This is why it's kind of this idea might work. And furthermore, you might notice that if we take instead of phi to be 1, this is what's equivalent to putting nothing here. This is why this I puncture is kind of equivalent to having no puncture. All right, so how are we going to go about to find it? Now, there turns out to be an expression for the 4-point function of this Liang model. So you can just look at literature and you can find the expression. It's some sum of a gamma function and a geometric function. I have not written it down here, not to overclutter the slide. And similarly, there are expressions for evaluating the S2 partition function of a 2,2 gauge theory. It is given again by some integral of a gamma function. Now what you can do is you can do the following thing. You can stare at this expression that you get for the S2 partition function, and you can play around with them and eventually find a 2,2 gauge theory whose S2 partition function matches the 4-point function. Yeah, I will next describe what is the 2D 2,2 gauge theory. You need to do that. before that, I do want to say one cell that I will mention. When you do when you compute the S2 partition function, there is a subtle issue in the fact that to preserve supersymmetry on S2, there are two different choices that you can do. They have to do with whether or not to couple your energy momentum tensor to the U1 axial current or the U1 vector, the U1 axial symmetry or the U1 vector symmetry. This is sometimes referred to as the B twist or the A twist. Now, the correspondence we mentioned assume that the S2 partition function is coupled using the axial symmetry, which is the B twist. However, the expression given here usually involves the A twist instead. This in particular means that the 2D theories I'm going to write down are not the actual theory from the reduction, but rather they are mirror symmetric to them. So to get the theory, you're going to have to replace the chiral with twisted chirals. All right. With that out of the way, the 2,2 gauge theory turned out to be this relatively simple theory. You have a U1 gauge theory, and it has 4 chiral fields that I've written down like this, that are charged on the U1 with the following charges. They have the following R charges. Here, the R charge is given by the left moving R charge, which is equivalent for the right moving R charge because it's a chiral field. Additionally, you also have 2 singlet fields that you turn out to need to add that have these R charges. They're a little harder to see that you need them. There are 2 specific ways to try to motivate you actually need them. One is that you kind of want to enforce these R charges, and the way it's usually it's impossible to enforce that if you just have these chiral fields. But if you also add the singlet fields, then you can enforce them to a superpotential. You can add this superpotential in that will enforce that you have this specific combination of R charge. That's one way to see why you need a flip field or the single field. There is another way to see it, and that is that you need them to match anomalies. As I mentioned, we can predict the anomalies of the 2D theory from the original 4-dimensional theory. So you can do this computation a bit more general without needing to specify the H0 theory. So I'll first do that and then specify the H0 theory. So we take a 4-dimensional n equal to 2 SCFT. We want to reduce it with a twist in the SU to R symmetry. First, you kind of want to understand how the symmetries of the 4D and 2D are related, particularly the R symmetries. You can work out by matching the supercharger that the R symmetry in the following way. Here U1I is the carton of the SU to R symmetry, and UR is the U1 part of the n equal to 2R symmetry. U1L is the left moving 2D R symmetry, and U1 right is the right moving 2D R symmetry. This basically just tells you that U1I become the vector like 2D R symmetry, and U1R become the axial 2D R symmetry. You can then do this reduction and compute the anomalies you get in 2D. There's particularly one non-vanishing anomaly. This is the trace of the left moving R symmetry square. This is equal to minus that of the right moving R symmetry square by 2,2 supersymmetry. And it turned out to be given by the following expression. Here A and C are the central charges, the ancestor of the 4D SCFT. G is the genus, N is the number of punctures, and this term is the contribution of the punctures that you have on the surface. Here I assume they are all the same and happen to be equal to the phi puncture. So this term comes from integrating the anomaly polynomial on the surface, and this one comes from the contribution of the individual punctures. All right, so these expressions so far were general, and now we can specialize the case we're considering here. First, we're looking at the H0 theory, for which we can use the central charge. This particular combination is equal to the number of vectors, and it's equal to this number for H0. G is equal to 0 since it's a sphere, and N is equal to 4 since there are 4 punctures. You can compute the contribution of the punctures from the boundary condition description, and you can show that they give you this number. This is simply half the contribution to the anomaly of a chiral field with R charge 3/5.
This equals to this case.
What?
These anomalies are all just equal.
No. This is so far it's general. This last step is specialized to the H0. If I choose a different theory, it will not be. But it happens for specifically for H0 and genus 0 and equal to 4, it's equal to 1. You can also try to compute it now in the 2D theory and show it happens to be equal to 1. If you particularly include these 2 singlet fields with a specific R charge. All right, so this model matches the S2 partition function. This model matches the linear correlator on the 4-punctured sphere, and also matches the anomalies. All right, you can now generalize to more general case, particularly you can generalize to the K+3 punctured sphere. And you can again do similar things. I won't bore you with the details, but you can eventually conclude that the two-dimensional gauge linear sigma model described in this picture does the job. Between the S2 paradigm of it, we match the correlator, given the known expression for the correlator on punched sphere. So, I was just about to do that. I kind of find it interesting that you're asking exactly where quivers appear. But all right. So notation, yeah. All right, the notation is usual quiver notation. The important thing is that these groups are unitary groups. So every one of them is a unitary group. This is also important for the following reason. If you have a unitary group, you can introduce a Heliopolis term. And that becomes a marginal operator in 2D. In particular, the number of groups is always equal to K, because this Heliopolis term span the conformal manifold that will give you this complex structure model of the torus. Besides everything else is as usual, these things are adjoint fields by fundamentals. These numbers here are the R charges that you turn out to need to put. Yeah. There is one other subtle issue here. There are some additional flip fields you're going to need to enter. So if when you have the U1, the adjoint of the U1 is just a singlet. So I think that some of these cases might also have something you can interpret as the adjoint for the U1, because there's some singlet field that are charged 3/5 in some of these models. I just didn't write down the singlets. Chiral, anti-chiral, yeah. Yeah.
Locally, many of them are forced updates.
Yeah, the R charges are however different. So there's some potential that breaks the. All right. Not in this class of model. This is what we have.
So the way you get this, that you get your correlator on the minimal model. This thing looks like the mirror of this.
You get the correlator of the minimal model. It in general has some large sum of terms that I think has usually gamma functions, some hypergeometric functions. So it's some of these things that have that structure. Now you want to interpret it as the S2 partition function of some GLSM. So
On model side and
yeah, you first of all, the way you match it is you match it with a different twist. So these models, you need to actually take the mirror of them to match the correlator. This is justified by the fact that the polynomial you uses the opposite twist. In particularly, the conformal manifold on the other side should be actual conformal, not twisted one. It should come from the superpotential, where in here it's come from the twisted operator. So this is where you have this issue. The level of computation, you just need to match the. Again, it's more complicated than I mentioned because of various subtle issues that I'm kind of ignoring here. But generally, that's what you do. And these models are actually the mirror dual for what you actually get in the compactification.
They have this relation between William-Mills correlators and the 3D manifold fields. So they were sort of similar, I think it's similar to the compactification of there was a sort of tricky too. We have correlators like 3D equal to vortex partition functions.
I see.
But anyways, somehow it looks like there is a mirror, and then we are taking some sort of GLSM limit on the side, similar boundaries for limit on the minimal model side. Types of functions that you, if I understand right, the thing that you have on the minimal model side is not written in terms of same functions that you have here.
Well, again, my understanding of this issue, I should probably say that I didn't do this actual derivation, it's what Matteo did. So I can only say what I understand of the derivation it works. You actually have collection of hypergeometric, they multiply the collection of gamma function and multiply hypergeometric function. The geometric function is the vortex partition function. This has to be given some integral over the chiral fields you have. Then it's evaluated by residues. And the residue will give you a sum of terms you get from the residue. And this sum of terms is what you actually match. So you kind of need to guess the structure so that you'll get the correct sum of residues. There is one subtle issue. That's the H0 partition function has an ambiguity. In general, the partition function on spheres is not completely physical. There is some counter ambiguity. For supersymmetric theory, in particular 2D 2,2, this is slightly elevated, as most of it is physical, but there is one ambiguity that has to do with Kähler transformation on the conformal manifold. Either the conformal manifold or the twisted one, depending on which twist you're using. This allows you to kind of change the prefactor of the entire partition function. So what you actually match is not the individual term, but kind of like the ratio of the term, because you can always make one term match. That's also why we start with a 4-punch, the 3-punch field, because you can just really absorb the entire number you get into this prefactor. Okay. I'll be happy to hear more about it, but maybe after. Okay.
About the changing hyperinterest, right? So it looks at this approach mirror between the two sides.
I see. Oh.
You talk about this mirror, but do you have a Lagrangian for the mirror?
No, the Lagrangian is just for this one. Of course, you can change the color to this color. The subtle issue is what you do with the vectors, because technically the vectors are described by twisted chirals.
Another question. It looks like, except for a small part, we will take the partition theory with electrical charge.
Well, the main thing that breaks it is you have these R charges that you need to take them different. So you introduce some superpotential that forces these R charges. For instance, in the U1 theory, if you look at the U1 model, it's the easiest way to do it. So if you ignore the flip field, because I even treated this thing I didn't treat down in the previous way, you can kind of think of these four as two hypers of the U1, and you can introduce, you can even take one of the flip fields as an adjoint. And then the model looks like an so, however, the R charges are not consistent with it. And what breaks it is the superpotential that I add. You cannot think of as something that is a 4,4. Okay. Anything else? All right. So we've introduced how we can find some general 2D 2,2 gauge theory that can match the reduction of H0 on a punctured sphere. However, this model looks somewhat strange. Normally, the way in which we can think of dimension reduction is we reduce, let's say, on some collection of building blocks, and we build the rest theory by gluing these building blocks together. Now, so for instance, I told you that I have this reduction on the 4-punctured sphere, and you get this U1 theory. I expect that I should take two 4-punctured spheres, glue them together, and get the 6-punctured sphere. But the 6-punctured sphere you find in here doesn't quite look like something you get from gluing the 2-punctured sphere. But it has a U2 gauge group, even though your original theories only have U1s. So this looks kind of strange how you can kind of understand, how can you kind of see the Riemann surface structure in these theories. There's turns out that there is a way to see the Riemann surface structure, and it's manifested in the elliptic genus. Particularly the elliptic genus of these theories has some specific, some TQFT structure. You can actually construct it by gluing various pieces as the same way you construct the Riemann surface. This provides some additional evidence that these theories indeed match the compactification of the H0 theory. We will see that they allow you to also do some rather interesting tests using what we mentioned previously to further kind of give further evidence for this claim. So that's what I will try to talk in, well, basically I think the 5 minutes I have left. All right, so I'll just try to at least talk. All right, I'll try to talk about it. I'll do it quickly, but this will be fun. All right, so first I introduce the idea. Can we introduce it on the 4-punctured sphere? So let's consider again the 4-punctured sphere. We have a sphere for 5 punctures. I can build it from collection of 2 3-punctured spheres. I have these 2 trinions, the other 2 3-punctured spheres, and I glue them together by gluing these 2 punctures. 4 of the punctures here will become the 4 punctures I have originally. They will be fixed to whatever puncture they have originally. However, there are 2 internal punctures, And it turns out for this construction, you need to sum over the two possibilities in the internal puncture. So they either be the phi puncture or the I puncture, the identity puncture. This might seem a bit strange, but it's quite natural from the correlator point of view, because then you think of this as breaking the correlator to some intermediate operator exchange, and you have two operators in the linear model, and then you can just sum over them. So the elliptic genus then either can be given in terms of sum of terms where you sum over all possible intermediate punctures. Now each term is made of specific building blocks given by this three-punctured sphere and the gluing you do between them. And you can associate with each one of them a specific contribution. So the full elliptic genus is you take all the contribution, you multiply them together, you get each individual term that way, and then you sum over all terms together. So that's the structure. And what are the actual building blocks you need? Well, it turns out the contribution of the actual building blocks are given simply by the elliptic genus of a free chiral field with some R charge. And here I've written down the contribution specifically. I gave down some of the R charge of the chiral fields you need. So if you take a sphere with a phi puncture, its elliptic genus is just a free chiral field with charge 1/5 and one with charge 3/5. Similarly, if you take two phi puncture and one I puncture, it's one chiral field with charge 3/5. This one is a little interesting. It turned out to be 0. So it's a completely empty theory without even the vacuum. And so forth with these cases. All right, so this turns out to be the building block. Now you can try to ask, how do we get these things? So one thing is simply by checking that this indeed works, that you indeed get the right elliptic genus. But there are still a few consistencies you can just do to show that these sort of building blocks do make some sense as compactification of the H0 theory. Particularly, you can kind of argue for this lower line in the following way. But first of all, these two cases describe the gluing process. They tell you how you glue phi punctures and how you glue the identity punctures. But we kind of already know how this gluing should be done. Right? I mentioned that due to the description of the boundary condition, the gluing should be done by reintroducing the field that received the Dirichlet boundary condition. And as you've seen before, for the phi puncture, you give Dirichlet to the field with charge 2/5, and for identity with the chiral field with charge 1/5. And these are exactly what you get. One chiral with charge 2/5 for these two, and the other one from the -1/5 when you go to the identity puncture. Now, this theory considers that you have three identity punctures, so you can figure out just reduction of H0 on S2 alone. And you can actually compute the elliptic genus of the reduction of H0 on S2 from this result by Gade Shlomo and Brian Willett. And where you use for the H0, you use the Moriyoshi Son Lagrangian. But you find this agrees with an archer with the elliptic genus of a single chiral field, which are 6/5. Yes. Yeah.
But you have this identity puncture. Why is the result dependent like this? This is like no puncture, you say. So why 3 no punctures is different from 2 no puncture? Like I would expect if it's no puncture, then the number of no punctures doesn't matter because
the number of no punctures doesn't seem to matter. So you can see here you have no punctures at all. Here you have 1 phi puncture, 2 phi punctures, and 3 phi punctures. Oh, it seems that the tubes are slightly different. The tube actually describe how you do the gluing, but they are not describing really tube as a surface with puncture. You really shouldn't think about this. This thing you can actually think about as surfaces with puncture. So 3 punctures, 2 and 1. It turns out to be equivalent, and we also show soon that it's consistent. But this one you really should think as you glue things. This is not a surface with 2 punctures, you glue 2 punctures. Oh, so the original way you get it is you just observe it happens to work. You actually, okay, once you have the 2-dimensional, 2D, the linear segment, you can forget about the correlate and you just work with the generalized segment. You can then compute the elliptic genus. It's interesting for various reasons that have to do with this matching for higher dimensions. The computation is done, you have this integral you need to perform, and you can evaluate using the JK residue. So you get a sum of the residues, and this sum happens to just mimic this structure. You can kind of argue that you can interpret it in this way. And once you have it, you can kind of argue that, okay, this makes sense because this thing you can think of as gluing in the prescription I mentioned before. This matches H0 on a sphere. And as I also mentioned, well, you don't really have a good derivation of these things from first principle, you can show that the anomalies can compute the anomaly of H0 on a 2 or 3 punctured sphere in the same way we did for the 4 punctured sphere. And it happened to match one chiral field 3 over 5 or chiral field 1 over 5 and chiral field 2 over 5. So normally happened to work with a specific content. Yeah, that is precisely this issue that I mentioned with the. You can say, okay, I can take I can just take the S2 partition function of this thing and match it to the correlator. The problem is in this case, there is no conformal manifold. The correlate is just a number. So the S2 partition can just be a number, but it's ambiguous because up to the p-factor is ambiguous. So you can just absorb this p-factor and change whatever you want with this ambiguity. That's why we cannot do it for the 3-punctured sphere. And the first case that you can do this non-trivial is for the 4-punctured sphere because then you actually have a conformal manifold. So there is some part that is non-ambiguous that you can use.
So a consistency check is, say I want to compute the 4 punctures here with I punctures. So I should take these 3.
This is what we're going to do?
I wanted 4i, but
I see.
because with 4 i's, it should be the same as with 3 i's, right?
This will work out. You can furthermore show that the number of 5 punctures won't change the anomalies. This will also work for other Alday-Gaiotto theories. It has to do with the way with the charges of the specific pointers with I. But what you can do is something similar to what you said. You can take 2 5 punctures and 2 I punctures. Formally, this should just be equivalent to this. So it should be equivalent to a chiral field 3 over 5. However, I can now evaluate it using the method. I can now break it to a collection of punctured sphere. And I can do it in 2 different ways. I can either take the phi I punctures on both sides, or I can take the 2 phi punctures and the 2 I punctures on the other side. Now, normally there is a sum here of phi and I. Here it just happens to be that because this specific 2b0, one of the terms drops out. I didn't write it down simply to not overcloud the slide, but in principle, there should be 2 terms here. One of them is a 0.
The tube is the chiral operator which does massive with the other linear, right? With the phi I linear.
Yeah.
They have charge sum.
Yes. Yeah, it's exactly happened that if you sum over all the charges, 2 of them are going to sum to massive field, and only one of them is left, so it will exactly get a chiral field out of 2 over 5. So both of them actually agree with a chiral field of out of 2 over 5. So you can show that you can not only reproduce with this thing the GLSM of this the ellipticness of the GLSM, but it also agree under all of these non-trivial checks where you try to change different number of punctures or try to do the Riemann decomposition in different ways. All right, so this kind of shows that there is indeed some Riemann structure surface Heidegger. It indeed seems to match with properties you might expect for compactification of the H0 theory. There is now one additional little game you can do with this thing. You can now use this elliptic structure and compute the elliptic genus associated with surfaces of genus higher than 1. So here we only found the model describing the compactification spheres. We didn't do higher genus present, but you can still use this structure to compute the elliptic genus for these surfaces, even though you don't have an actual GLSM model for them. Here I've written down the expression for various values of genus, starting from 2, 4, and 8. So here I'm thinking of the elliptic genus as an index for a 0,2 gauge theory. There are 2 parameters I'm using here, Q and Y. Q kind of the dimension of the operator. You can think of it as an analog of X in 3 dimension or a PQ in 4D if you're familiar with indexes in 3D and 4D. And here I'm expanding in Q, similar to how you expand in PQ or in X in 3D. Why is the fugacity associated with the left moving R symmetry? From the 0 point of view, this is a flavor symmetry, so I can just refine it by a fugacity, which I'm using Y. This means that the power in this fugacity Y is the R charge on the left moving R symmetry. All right. So these are the expression. I don't know if you can notice some specific regularity in these numbers. With the shortest of time, I'll just tell you the answer. It turns out that the elliptic genus, at least for sufficiently large genus, in this case it happens to be G bigger than 7, the genus become this expression. So it's a statistic exponential, so you basically take all possible products of the terms in here, but describe otherwise by precisely 4 terms. Now, you may notice that you have 3G minus 1 operators contributing this way to the elliptic genus. Why 1 means that its R charge is 1, and square root of q mean dimension is half. These are the properties of a marginal operator. But this will agree with having 3g minus 1 marginal operator. I should also mention that here I've switched y to 1 over y, so I switched essentially did this mirror symmetry on the elliptic genus, which is why you get you actually get a conformal manifold rather than a twisted one. So it matches with what you expect from the Fourier reduction. Now, this one you get R chart that is negative, minus 1 over 5 and minus 6 over 5. And the dimension is agrees with a twisted chiral that has this specific R chart, either minus 1 over 5 and 1 over 5, or minus 6 over 5 and 6 over 5. This happens to be exactly what you expect from the reduction of H0 on higher genus Riemann surface. You get 3g minus 1 from the energy momentum tensor, which you can associate with the complex structure model of the Riemann surface. And then you have this contribution of the twisted chiral that come from Coulomb-Chopper dimension 6 over 5, precisely the one you have in H0. You can notice the multiplicity is 1 minus g, exactly as you expect, because these are argued previously. Oh, it turns out you get 2. It's something that you can do when you take the 4dn equal to Coulomb-Chopper, and you can decompose it to 2,2 representation. The ground state will get you 1, with dimension is 6 over 5, with dimension is Coulomb-Chopper, but then you get another one from some descendant that happens to have minus 1 because you operate with two supercharges. So it reduces to the left and the right, so that you just get this one. We just happen to do this reduction. This is the component you find it behave this way. Right, I should probably hurry up. I should just mention briefly that for small lower genus, you do get deviation, but different appears to be very regularly. Particularly deviation of this, you have a lot of operator that looks like this, coming from basically product of these operators. And this appears to agree with this formula, at least as long as this product k is smaller than g minus 1. So you can see that as when you increase g, you increase the order in which you get agreement, but at some point there will be deviations. And it seems to be very regularly for reasons we don't really understand. All right. Before concluding, I will probably just try to say 2 more things briefly. One thing is regarding the physical interpretation of this result. So I've noticed that the elliptic genus obeys this sort of structure with the Riemann surface. However, it's still a bit strange as to why it actually obeys it. The normal interpretation would be that you just build the theory by gluing the various pieces physically. However, the structure that I've shown doesn't seem to correspond to actually physical gluing. You get a direct sum of theories, each one is just a fake chiral field. It obviously doesn't quite look like the GLSM we originally started with. What seemed to happen is roughly the following one. The elliptic genus of the GLSM appears to receive contribution from only a finite number of special points on the moduli space. To this that I've drawn here the moduli space of the 4-punched sphere theory, so this U1 with 4 chirals. It happens to consist of an S1. Oh, I've also introduced a Ferrari-Leopold term to regularize the moduli space a little bit. So it has an S1 whose radius is equal to the square root of this Ferrari-Leopold term. And there are 2 special points, one where you have a 1-dimensional cone emanating from it, another one where you have 2 1-dimensional cone emanating from it. It turns out the elliptic genus will just get a contribution precisely from these 2 special points. Locally, if you zoom around this point, the theory describes a collection of free chiral fields, and the elliptic genus is just a contribution of these 2 free chiral fields. So it seems that what this sort of TQFT structure does is it kind of just to pick up the contribution precisely from this point. So you have this sum of different terms. Each point in the sum corresponds to one of these points, and the chiral field just from this point is the low, the low in the theory around those points. And this is true also seems to be true also for the IGLSMs. So then you just get naturally a sum of this points. It's one from these points. You can also notice if I take the Ferrari-Leopold, if I change the Ferrari-Leopold system, I can make the distance of this point go larger. So there's a natural limit which these 2 things just decouple, and you kind of think of breaking the surface into the original, the two trinions.
By the process theory on a circle to 3D, that gluing is done by integrating over the real mass parameters, or integrating over the Coulomb branch. And here, like, there are special points that you're summing.
Yeah, it kind of looks like the integration over the, well, at least the normal gluing to integrate over the flavor symmetry is kind of done by summing over the puncture. Like like introducing the background flavor some background for the flavor field is covered by the choice of the function, and then you just do this sum. And here it seems to be interpreted by this sort of sum over vacuum.
Like, and you integrate over density, like things, so like parameter somehow associated to the, like some value of some Wilson line or something.
Maybe. We know that there is this parameter, you need to give what sort of pointer you have, and similar to some of them when you do this gluing. It doesn't seem to be like you're gauging a discrete symmetry, because you don't need to divide by the order. It's possible that there is some other way of thinking about it, like some reason we haven't really thought about it that far, so it'd be interesting to consider if you have some idea.
Related to Chicago's comment, so each primal is correspondent to this different values of the Wilson line. So
What?
you have two
Yeah.
operators, I and I, they both correspond to the distinct Wilson.
Well, they seem to correspond to different boundary conditions, seem to be coupled to different functions. Yeah, I don't know if this one. It really is in the C-star action. It's how the U1 R symmetry is embedded inside the S0 that rotates them. So they kind of look very similar to one another. But this thing leads to the fact that the R charge of the field you're gluing is slightly different, and then the anomaly contribution of the point is slightly different. So they kind of look different, but they might still seem similar, so maybe you can interpret as some additional parameter that you introduce. So I don't have anything more to say about this. All right, I should probably start to conclusion because I'm really run out of time. I'll just briefly say that this still isn't quite the same as the actual physical description that allows you to glue the theories. You can allow to reproduce the GLSMs from another one. And also, therefore, you cannot do things like complete the S2 partition function using this thing. There's some complications there that I don't want to get into right now. I will finally just briefly mention generalization. You can think of the H0 theory as the rank 1 case of an infinite family that is known as the A1, A2 R Douglas theory, whose rank is R. The nice thing property of this family is that its chiral algebra is also a minimal model. So it in general be a higher minimal model, so usually it has more isolated representation of the Ross algebra, but it's still a minimal model. So in principle, you can still be able to do the computation. We at least checked that you can reproduce, you can generally predict at least to the A1, A4 case. And it works very similar. You can find GLS and engineer the 4-point function. The elliptic genus has a similar TQFT structure, and many of the things I mentioned seem to work out also in that case. We expect it to behave similarly for higher values of R, but we haven't checked it explicitly. All right, so concluding, talk about that dimension action can lead to surprising relation between field theories in different dimensions. Particularly interesting is HG type relation, where partition function of different theories seem to agree. And this can be understood as both sharing some higher dimensional origin. We've seen that specific case, if you look at a 4D n equal to 2 theory, it's natural to expect that relation between the reduction of that theory on a Riemann surface, 2,2 theory to get, and the chiral algebra of the theory. In particular, for the case of H0, we have suggested a relation between the reduction of H0 on the 2D 2,2 theory, get reduction H0 on some surface sigma, and the sigma, the S2 from that model, and the sigma correlate of the Lee-Yang minimal model. We've seen that you can employ this to understand the reduction of the H0 theory on sigma, particularly on two-dimensional surfaces, particularly on punctured spheres. And we've seen that they can be tested by reverse consistency check, and particularly when the elliptic genus has a natural structure that can be given by using the Riemann surface, which also seem to agree in very non-trivial ways with what you expect from the action of the H0. There are several open questions. First, I mentioned if we want to better understand the gluing, we want to know if there is some physical way to actually get the GLSM from gluing models. Also, we need to better understand generalization to the A1, A2, A2 that seems to be natural to do. Then you can be a bit more ambitious and try to wonder if you can do also more general and equal to SCFT, whose chiral algebra is not just a minimal model. And finally, I've noted that there is an interesting regularity in the relation between the operators of the 4D and 2D theories. But so we can understand something about the operators of the 2D theory from the 4D theory, but there are some mysteries there that do seem to require understanding. So this might be interesting, especially if this specific class of theory seems to be sufficiently simple that you might be able to understand this, which would then have interesting implications also for other compactifications. All right, so I think I should probably stop now.
What's the problem with A1, A1? And the second one is, suppose that you take H0 Douglas with a non-trivial global symmetry. How does it affect the puncture structure?
Okay, problem with there is in principle no particular issue. I guess we just the natural generalization is to A1 even because then you just get the minimal. It's a very similar minimal model. I don't remember by heart what you get for A1 A odd. It's something again. It's not something remarkably. I don't think it's more complicated, but it's just a little different. So you haven't considered it. You can probably consider that as well. But the kind of thing is when we go behind the H0 Douglas, I think we kind of thought about something else, like n equal to 4 or other things. So we cannot say we looked at that. Now, the other question was flavor symmetry. Again, there doesn't naively seem to be anything wrong with having a flavor symmetry, besides the fact that it might make the chiral algebra a bit more messy. But as far as reduction is concerned, there is nothing wrong. The only complication is that you can now add flux sources for the flavor symmetry. And then you have more options. Well, are that good or bad? Of course, it depends on your outlook, I guess. Well, the puncture themselves, you can put flux in the flavor symmetry itself. So that can get you to 2,2 that don't also specify just by the genus of the surface as they are now, but also by the flux in the flavor symmetry. And depending on how large the flavor symmetry, you have more options. Now, the puncture will be somewhat affected. They will carry the flavor symmetry. You might need to break it for the puncture because of the boundary condition. But then you'll just have but then the puncture might break the flavor symmetry depending on specifically what you have in the low energy. They will, of course, change the anomaly that you might have for the puncture. There can be a mixed anomaly between the U1R and some U1 subgroup of the flavor symmetry, and the puncture might have some contribution to that.
So if I understood this wrong. So for this general A1, A2R theories, would the statement be that the functions that are involved, well, the clues that are involved, you read off from studying like the H moduli space at finite R, and then looking at what possible sort of points you get where you're getting the effective.
Can you repeat the
So
question?
for A1, A2,
yeah,
you sort of go to the result by like Andy and so on, who studied the H moduli space and realize there are two low sides if you look at the stratification. And then those corresponded to your identity function and your phi function, because these two different C star actions that you had.
Yeah, the way I think about it is you reduce it to 3 dimensions. So if you do that naively, you just get a free twisted hyper. That was known by this work of Dan Shi. But it's been recently known, it has to do with relation with the VOAs, that if you keep the circle finite, there turn out to be some number of finite points where you have these and then the behavior in this point is very similar, but they differ by the relation of the C star. There's an answer that rotates the puncture, how to the U1R symmetry. And then they seem to define puncture that looks locally very similar, but because of this correspondence, their anomalies, for instance, will be slightly different. And then the output of the gluing field will be slightly different. This observation also generalized to, for example, the higher cases. But that's at least what we have so far.
So you stop the unitary theory and then put it on a sphere, and you have 2D match, and you kind of how you get.
Oh, you mean now you get the non-unitary? I can't really give you a very good explanation. That's one of the reasons why I said I'm going to assume this works. But there is a rough argument. And it's basically, first of all, the chiral algebra itself, which is funny, is a non-unitary 2D theory. That has happened to work in this way. My understanding, at least, again, it might be wrong. I'm saying that this is my understanding of the thing. You take the theory on the S2, you do the omega deformation. That will, you kind of think of a different way to build it. You can also think about the hemisphere. I'm going to do the S2 form it. It's probably not the right way to do it, but for simplicity, I do the S2. You put the omega deformation, so you localize your theory at the origin. That effectively means that your 4D theory lives kind of at this original, And then you also introduce a U1 outwards. That kind of fixes that would preserve the 0,4 part of the supersymmetry. That construction kind of fixes the subgroup of adjustment. It is also the one present in the 2D chiral algebra, which I think lives on the non-supersymmetric side. And then you kind of expect that the natural theory to get is the chiral algebra.
Different from the usual agent.
Yeah, it's
There you get the unitary.
yeah. Again, it seems to be similar. I'm not exactly sure why you get this difference, I admit.
Gabi,